Yeah, once again, good evening, all of you. And Mohammed Aftab, good evening. Mohammed Aftab, good evening. I think you are not able to unmute your mic. Okay. So, first, I would like to share my screen, and my entire screen is visible. Okay. And this is my MATLAB window, and along with I need to. Okay. So, this is the method which I prepared a PDF file, and I shared the same file in the WhatsApp group so that you can easily go through. Usually, this Crank-Nicolson method we use for partial differential equation. Okay, but also the same method in a different way we can use for ODE. Okay, and there are two different ways to use the same. See, this is the basic introduction. The Crank-Nicolson method is numerical technique used for solving ordinary and partial differential equations. It is a finite difference method that combines implicit and explicit time-stepping schemes to achieve second-order accuracy in both time and space. The method is particularly popular for solving parabolic partial differential equations such as heat equation, diffusion equation, and certain type of reactions. Okay, diffusion equations. So this is overview about this method. The Crank-Nicolson method approximates the derivative in the differential equation using central differences at both times and time levels, leading to a set of algebraic equations that can be solved iteratively. And the method discretizes both time and space dimensions. The context domain is divided into discrete intervals, and the derivative are approximated at the midpoint of each interval. The Crank-Nicolson method uses a weighted averages of the explicit and implicit scheme. It evaluates the right-hand side of the equation at both the current and the next time step, resulting in a tridiagonal system of equations that can be solved efficiently. And mainly, this tridiagonal is used for when we have partial differential equations, okay, specifically. But sometimes we can use this tridiagonal system for the ODE also. And the method is unconditionally stable for linear problem, meaning the time step can be chosen independently of the spatial discretization to ensure stability. And the Crank-Nicolson method offers a second order accuracy in the both time and space, making it more accurate than purely explicit or implicit method. And there are several applications we can see for to solve different type of problems. The Crank-Nicolson method is commonly used to model diffusion phenomena such as heat conduction in the material or separate of a pollutant in the environment. It is also applicable to reaction diffusion system where chemical reactions occur along with the diffusion process, and the method is used in option pricing models where it helps to model the diffusion of underlying asset over time. And while less common compared to the other method like finite volume or finite element method, Crank-Nicolson can be applied to certain type of fluid flow problems. Okay, so here is the approach which in section second expand about for the ODE. Okay, and this approach we can easily use to solve the ordinary differential equations. Okay, so the Crank-Nicolson method is the same basics are given here. It is an implicit method that offers improved stability and accuracy compared to explicit method like Euler method. Okay, so this is the overview. You can see in the very first equation, we have the problem statement. Consider the first order ordinary differential equation dy upon dt is equal to fty. Okay, and y is the unknown function of t, and fty is a given function. So first, then after we will discretize, divide the interval, t naught to t into n sub intervals. Okay, and delta t will be equal to t minus t naught upon n, where ti, the step size or the points we can compute following this, ti is equal to t naught plus I delta t. Okay, where I will be from 0, 1, 2, and up so on, and all the point, the interval which will be divided into sub intervals following these points. Okay, and we will approximate the solution yt at each time point ti is yi is equal to approximate to yti. Okay, so this is approximate, not the exact. Then after we have the central difference dy upon dt approximated to yi plus 1 minus yi upon dt. Okay, so this is the central difference which will be used, and the Crank-Nicolson scheme for this or by using this central difference, which will be using the difference approximation for both forward and backward difference, and the scheme is given in this equation. So this equation is very important, as I told you that in all the methods which we are discussing for the computing, we should have in iteration form. Okay, so that we can easily employ the same to write the MATLAB code. So this equation will help you to write the MATLAB code, and this can be, we can rearrange to solve yi plus 1 is in this way: yi plus 1 minus delta t upon 2 f ti plus 1 yi plus 1 is equal to yi plus delta t upon 2 f ti ya. So sometimes we can use this equation also. So either you are using this equation or you are using this one. Okay, so this is also can be used in this way. Yi plus 1 is equal to yi and plus delta t upon 2. Okay, and then we have f ti yi plus f ti plus 1 and yi plus 1. Okay, so in this way we can use. And what about this one? This is the slope at the point ti yi, and this is the slope at ti plus 1 yi plus 1. Okay, so this expression sometimes we can use. So the iterative solution, since the equation is implicit, it requires iterative method such as we use Newton's to solve yi plus 1 at each step, and apply the boundary conditions whatever we are given, t naught or tn depending upon the problem, and we have to repeat this iterative process each time step until reaching the desired endpoint. And there are several applications also we try to explain here. You can go through the detail. Okay, now come to our MATLAB part. So I put here two examples. Okay, come to very first example. The approach is very quite simple. We have this differential equation. Just 1 minute, I have to open. 1 minute, please. Okay, so we have this is the differential equation. dy upon dt is equal to fty, and suppose that dy upon dt is equal to fty is equal to minus y. So this is the differential equation, and we have along with the initial condition y naught is equal to 1. Okay, so we will start, and we want to compute in the interval 0 to 10. So this is the initial condition, and this is the end condition, end value of the interval. Okay, and the step size we are choosing, we want to divide this interval from 0 to 10 in 1000 step size. Okay, this is the value of n. This is the value of n as we discussed in the method. And delta t will be equal to t end minus t start upon number of step. According to that, the value of delta t will be computed. And this is the initial condition, y naught is equal to 1. That is corresponding to the given differential equation. Okay, and we will write this differential equation in just like erroneous function. Okay, so f will be equal to at the rate ty minus y. Okay, I think all of you know about this anonymous function. So f is a function of t and y. Okay, and the meaning of at the rate, the variables or the parameters which are involving in the function, you can see at its place. Okay, so we will write all the parameters or the variables which are involved in the dy upon dt. So dy upon dt is function of t and y. Okay, but is equal to minus y, is equal to minus y. So this is minus y. Okay, so fty is only the function and is equal to minus y. So this is the anonymous function and we can easily use. Now, for the Crank-Nicolson method, we need y zeros, y vector, okay? And that will depend upon the length of t, length of the t. So what we have done at this place corresponding to these values. So here are the number of steps which we choose at this place are 1000, okay? And then if these are the steps, then number of the point will be one more plus one. If we have, okay, so this is one step, this is the other, this one and this one. But the number of points will be one more. Okay, 1, 2, 3, 4, but the points are 5. Okay, so that's why the length of these y zeros will be 1 to number of steps plus 1. And this is the initial value. So everything about this statement already explained in the previous methods, and here this will generate only the empty vector. All the elements will be zeros, and these will be updated by using index. Okay, so y1 is the first value or the given value. This is the initial value. So we will initialize by giving the index. Okay, so this is the first value y1 and 1 is the index. Okay, y naught, and with the value of y naught is we have 1. Now we will implement our approach to get all the values. Okay, so yes, come here. So this is the Crank-Nicolson update formula. Here we will update the values which will n will start from 1 to number of steps. Okay, so here is the iteration. Tn will be equal to n minus 1 into delta t, and Tnp1 will be equal to n product delta t. Okay, so from this all the values t naught, t1, t2, t naught is given, t1, t2, t3, t4, and so on. All the values will be computed. And now this is our main formula which we need to implement. Okay, see now here, this is the right hand side. This is the right hand side of the formula. Okay, we have to come back in the formula so that you can easily compare. Yes, so here is, okay, just 1 minute. Yes, you can see this is the right hand side. Okay, you can see this is the right hand side. All this one has been used, this one. So here is in the MATLAB at the rate, this is the function, this is the function, and on the right hand side we have is yn, then plus 0.5 delta t. 0.5 means delta t upon 2. So 1 by 2 is 0.5. Okay, 0.5 delta t, this is the delta t, and here is ftnyn. Ftnyn means this value. See, ftiyi. In the place of I, we are in the MATLAB, we are using n. So this will be ftnyn. Okay, see here, this is ftnyn. Then this is the next value. Next value, tn plus 1 and yn plus 1, that is computed here. Okay, and then we have, sorry, yes, just 1 minute, why this page is opening. Okay, So this is the complete right hand side you can see, and y minus y and p1. Okay, so this is the complete the entire Crank-Nicolson update formula. Okay, so from this place we need to update the value yn p1 yn plus 1. Okay, so the yn plus 1 will be stored at this place. The entire value will be computed here and will be stored in right hand side, which we are using here. Okay, so f0's right hand side corresponding to yn. Okay, so here we are using function zeros, f0's function. So what this will do, f0's function, all the values corresponding to index which will start from n equal to 1 to number of steps. Okay, so first value is from this place will be stored at this place when we have n equal to 1. Okay, so y2 will be computed and so on. The loop will execute and all the values will be computed, will store at this place, and corresponding to the index when these values will be calculated or computed will store in yn plus 1. Okay, so this is the entire procedure to implement our Crank-Nicolson method. Then after, when the values of y corresponding to t vector will be computed, then we can easily go for plot the function. And to plot for the same, what we do, we need t. This is the line space. Okay, and as you know, the vector t and y both must have equal length. Okay, so here we are taking the line space for t, which will be t start and t end. Okay, the initial point and last point, but the number of step will be but the points will be number of step plus 1. Okay, 1 point will be more than number of step. So these are the total number of points for the interval, for the given interval. Okay, and the length of both t and y must be equal. And when you will check the length of t as well as length of y will be equal, and only then this plot will be possible. And when you will execute for the plot, here is plot function ty, x label, y label, z label, sorry, title and grid on. So these are the same statements which we are using for the labeling. Okay, and now you can execute this statement. Okay, and when you will execute, we will have a very nice graph. Yes, so this is the solution of ODE using this method which we now discuss here, Crank-Nicolson method. Okay, so this is the approach, and you can choose the same for different type of problem. You can do numerous experiments. You can just see if you are taking at this place some more example, like here this is for dy upon dt is equal to minus y. Okay, and if you are comment this statement control r, sorry, and we are taking at this place one more function. Here is control v, sorry, control z. F is equal to at the rate ty t comma y, and we have suppose that y product exponential, you can choose here t also. Okay, here is t also. So this is one new function, dy upon dt is equal to y exponential t, and when you will execute, and the initial condition you can change whatever we are given. We have this graph, you can see we have this graph for this function. So the program which we write at this place, you can do several experiment by using this approach. Okay, but here this example I will not recommend right now, because this is here we are using tridiagonal matrix. Okay, so this tridiagonal matrix will be discussed after the method finite difference. Okay, so along with this will be discussed. So I will not recommend this example, but you can use this approach for different type of problems. Okay, you can try yourself more. Any question, please, related to this one? I don't understand the method properly. Uh, okay. This is the question in the beginning. Okay. So, please let me know if everything is clear related to this method. Any question, please? Please, any question? Okay, Nalini, you are saying you understand now. Okay. Any more question, please? So if all the methods which we discussed from in the beginning to till now, okay, if all of you are able to convert every method in iteration format, okay, because we need to apply iterative approach in MATLAB, and then you can easily convert every equation into MATLAB syntax. Okay, so this is the our main method, main formula, which we convert in MATLAB syntax, and the other part you can see which we discuss here are same as we do in other methods. There is no difference. Okay, and along with you can write this method in user defined. Okay, if you want to convert this approach in a user-defined function or user-defined method function for numerical approach, you can do. Okay, but once you are able to apply this for loop to get all the values and how we are using, only this part is important in every method. So the other part which is at the place the initial value, uh, first value of the interval, last value of the interval, step size, h, delta. Okay, all these are similar, nothing new. Only the new part is when we are going to discuss about the method, and this is only the formula.
Excuse
And
me,
this
sir.
part is also not new. Yes, please.
Sir, line number 24 for the program.
Line number 24.
4.
Okay. Once again, I have to share my screen. Line number 24. Yes.
Yes, sir. Sir, could you please repeat the term why this NP1? What is this, sir? NP1.
NP1. Okay. NP1. See, come back. Come back
Sure, sir.
here. See this equation number 2 at this place. Here is we are using FTIYI. FTIYI. And in the second part, we have FTI plus 1, YI plus 1. So when you will catch this equation and then come here. So this is TIYI. Okay. This is Ti plus 1 and Yi plus 1. Got it?
Sure, sir. Sure. Done, sir. Thank you.
Okay. So just I am again repeating the same. You need to convert the formula in MATLAB syntax or how you are using. Not necessarily that I use at the place yi plus 1. Okay. You can simply use in another way. Okay. So here n means I and p means plus and 1 means 1.
Actually, sir, I confused due to that. This line number 24, there is this delta T star F of T and comma Y of N. This Y
Okay.
of N confused me. That's why, sir.
Okay.
Thank you, sir. Thank you. Thank you.
Okay, great. So that's why I shared the file yesterday. I thought that today I am not able to take the session, but if I will share the content for this method, this will help you to go through and you will try yourself. If there will be any kind of question or the problem, you can discuss with me. Okay. So I think now everything is clear. Now what you will do several examples or different methods. And also, I did not to make one more part at this place. As you know, we convert these methods in user defined. Previously, we convert every method in 2 or 3 different ways. Okay, but here I just demonstrate only the method how you can implement in this single script file. Okay, you will do now yourself to convert this sequence of statements in user defined function as we do for the other methods. Okay, you can represent this example number 1 in 2 different way also. Okay, as we do in the beginning. So this part is up to you. You will do now yourself. Can you do? You will try yourself?
Sure, sir, sure.
Yeah. So the method which we need to discuss today finished within 40 minutes. Okay. And tomorrow we will come with the new method. If you have any more question, please. One more thing I will let you know. Today I will upload some quizzes assignment and you will log in and then you will complete the same. And tomorrow will be there. Okay. If you have any question, any problem, please feel free to discuss so that we can now end this today's session. Any question, please? No question. Okay. So the content already I shared in the WhatsApp group. Script file is there. You must try. And tomorrow we will come with the new method. Okay. So today I prepared 2 examples, but the second example not suitable for this approach. Okay. So that will be discussed in the next method when we will discuss about finite difference. Okay. So thank you for today's session. If you have question, please feel free. Otherwise, it is time to end the session.
Thank you, sir. Thank you.
Okay. Thank you and good night. Tomorrow we will come with the new problems. Okay. So good night. And now I am going to end the session.
Thank you, sir. Good night.
Thank you, Mohammed Bakir, and all the participants.